Okay, so this is the first of two pre-recorded lectures for the week of February 27th while I'll be away. So I'll be covering Taylor and Maclaurin series. Now, although these topics are part of although they're part of Module 2, that's on power series, because Taylor and Maclaurin series themselves are power series, I want to emphasize that this particular material will not be included on the midterm because homework for it will be due sometime after. Okay. So at this point of a course, you have seen how power series for certain functions can be obtained. The basic idea is that the function is somehow related to a geometric series by some small modification, or maybe by differentiating or integrating or multiplying by power of x, or substitution of a power of x, something like that. But there's so many functions that can't really be related to geometric series in that way, without, or at least not without considerable difficulty. So it'd be nice to have some more general approach to obtaining a power series of a given function. So we're looking at getting a power series of this form for some unknown coefficients Cn and some chosen center x naught, given some function f of x. And trying to get a power series for f of x in general is what leads to what is called Taylor's theorem. Now, suppose I cut off the series after a certain point. So I start from term number 0, go all the way up to some upper limit, what I'll call n. Please keep in mind that I've changed the index variable to j here instead of n here. So what we have here are powers of x minus x naught from raised to j power from j equals 0 up to n. What that means is this whole expression is a polynomial of degree n. So then, if I substitute x equal to x naught, all of these terms will be 0, except for when j equals 0. So I end up just getting c naught. So what that means is c naught is just the value of this polynomial at x naught. Similarly, suppose I take the derivative of both sides of this equation. So I'll get Tn prime of x on the left, and then on the right side, a term involving C0 will go away because that's just a constant term. Actually, to help you see this more clearly, I'm going to write out the first few terms. So we have C naught plus C1, x minus x naught plus C2, x minus x naught squared, and so on. So if I take the derivative of this with respect to x, so this term goes away, I get C1 here, and then I get 2C2 x minus x naught to the first power, and so on. So what will happen is, if I then plug in x equal x naught in the derivative, remember this term that you take a derivative, you get C1, that will stick around. All other terms will go away. So, and you can try working this out yourself to be sure, but Tn prime of x naught turns out to be C1. Now, if I take the second derivative, so on the left side, I'd have Tn double prime of x. And if I take a second derivative of all this, well, second derivative of all this will be 0, just because the second derivative of any linear function is 0. If I take a second derivative of this, first derivative gives me 2c2 times x minus x naught. And then I take the derivative one more time, and I'll just get 2c2. So that turns out to be the second derivative at x naught. So we see starting to see a pattern here that by taking derivatives and evaluating at x naught, we're getting the coefficients. So more generally, if I take the jth derivative of Tn and then plug in x equals x naught, that's what this vertical bar means. I'm plugging in x equals x naught. So that's the jth derivative at that point. What I'm going to get for any value of j is j factorial times cj. Like if I continue this process, like the third derivative, so I'd have additional term c3 x minus x naught cubed. If I take a third derivative of this, the first time I take a derivative, I get a 3 down here, and then I have x minus x naught squared. If I take a derivative of that, an additional 2 would come down, so then I'd have 6 down here. So the third derivative is going to be 6 times c3 when you plug in x equal x naught. All right, so in general, it's j factorial times cj. Now, Tn of x is a polynomial of some finite degree. But what if I just let n go off to infinity? So then if f of x has every derivative defined at x naught, then this fraction right here gives me my coefficients. So this is Cn. So this is the formula for a power series of a given function f of x centered at x naught. So this series is called the Taylor series of f with center x naught. And then in the special case of x, if x naught happens to be 0, it's still called a Taylor series with center 0, but it's also called a Maclaurin series. So the Maclaurin series is only for the case where the center is 0. And we'll be working with Maclaurin series most of the time, but in occasional examples, we'll do with a Taylor series that has a different center. So for any functions that we've seen before, when we were able to get the power series for it, for a given center, that also was a Taylor series. It's just that now we have a general formula for all the coefficients. So here's an example. For function is e to the x. So as you know, the derivative of e to the x is just e to the x. So if I want the Maclaurin series, I'm going to use this formula where my function is e to the x and my center is 0. So what that means is I'm going to be evaluating every derivative of e to the x at 0. But that just means this numerator here is going to be e to the 0, which is 1. So all I'm going to get is this part, so that gives me x to the n, because the center is 0. And then I'm dividing by n factorial. So this is the Maclaurin series for e to the x. So it's a sum n equals 0 to infinity of x to the n over n factorial. As I mentioned here, every derivative of e to the x is e to the 0, which is 1. It can be shown using a ratio test. I think I might have shown it previously, that this series converges for all x. So now we have a way of obtaining the power series for any function. But the existence of a Taylor series assumes that a function has infinitely many derivatives, that all those derivatives are defined, which is not true in general. And if we're going to use a Taylor series, of course, we can't use infinitely many terms in any practical computation. You have to cut it off after a certain point. So one thing we'd like to know is, if you are going to use the first several terms of some Taylor series for some function, how accurately does that approximate the function? If you're going to be tossing out all terms past a certain point, you're inducing an error. So how large can that error be? So this leads to trying to estimate what's called a remainder. So that's, if I'm use Rn of x to refer to remainder, that's equal to f of x minus the truncated Taylor series. So that it's a partial sum of a Taylor series taking all terms up to degree n, but it's also known as the Tn is also known as the nth degree Taylor polynomial of f with whatever center you have. So if we can figure out this error, which is known as the Taylor remainder, thus the letter R, then we know how accurate our Taylor polynomial will be. So first we're going to look at some simple cases. So the simplest Taylor polynomial you can have is T0 of x. So it's just a constant function, Taylor polynomial of degree 0. And that's just equal to f of x naught, where x naught is whatever center you've chosen. Of course, it's not a very accurate approximation in most cases, but that's not the point. We just want to see how far off we can be. So what I can do, I have a fundamental theorem of calculus. I have this equation here, f of x equals f of x naught plus this integral from x naught to x of the derivative. Keep in mind, I'm using f prime of s ds inside the integral. I can't use x because I have x as an upper limit. So this right here is my Taylor polynomial. So whatever's left is the error. So this is a remainder. Now, this is not a very helpful form of a remainder, but what I can do is use a theorem called the mean value theorem for integrals. It's something that may have been covered in Cal 2, or it should have been anyway. And what the mean value theorem for integrals says is that this integral is equal to the integrand evaluated, whoops, didn't mean to do that. This integral is equal to the integrand, f prime, evaluated at some unknown point that's between the two limits times the difference of the limits, x minus x naught. So this is an alternative form of a remainder. So what it says is the error in approximating f of x by f of x naught is given by the distance between x and x naught, or this displacement, if you will, times the derivative at some point in between. So if you have an idea of how large this can get, then you can come up with an upper bound for this Taylor remainder. Now I want to point out, if we go back a little bit, like if I write out the first few terms of this general Taylor series here. All right, so the first term is f of x naught. The second term is f prime of x naught, x minus x naught. And then I'll do one more, 1/2 x minus x naught squared. I still need the second derivative. Okay, and so on. Okay. Notice the second term here is f prime of x naught, x minus x naught. Now look at the remainder in this case. That's f prime at some unknown point xc. This is a Greek letter xc, which I also refer to as squiggly, times x minus x naught. So this remainder actually resembles the next term in the Taylor series. It's just you have a derivative evaluated at a different point. So now I'll continue. Here's my first degree Taylor polynomial. So we've include the second term of a Taylor series. Again, note the similarity. So now This is called the tangent line approximation of f at x naught. So this function gives you the so y equal to this is the equation of a tangent line to f at x naught. So you're approximating f near x naught by a line. So now I want a remainder, f of x minus this tangent line approximation. So to do that, I'd apply the fundamental theorem of calculus twice. Okay, what I'm going to do is I'm going to include an additional step. I'm going to grab what I had earlier. Hold on. I'm relying on the fact that since you're watching the video for this, and you can back up and rewatch or pause or whatever you need to do. Okay, so this is what I had before, f of x naught plus its integral of a derivative. But then what I'm going to do is I'm going to replace this derivative with this, again, applying a fundamental theorem of calculus. So now I have f prime at the same point x naught plus an integral from x naught to s, because s is what I'm plugging into the derivative here, of its derivative, which is f double prime. And I need to use a different letter because I'm already using s. So then what I can do is I can break this outer integral up in two. And now this integral, remember, f prime of x naught is a constant because I'm integrating with respect to s. And we don't have s in this function at all. So this integral, I can just go ahead and evaluate it, and I get the next term in a Taylor series. So then what's left, so this right here, notice it's exactly the same as my t1 of x up here. So what's left over has to be, well, the remainder. But now I need to try to evaluate this as best I can. And the best way to do that is if I interchange the order of integration, so then I have f double prime of z can be moved outside the integral. Well, actually, sorry. I'm not interchanging any order of integration just yet. Notice that f double prime of z since that does not depend on hold on a second. Okay, sorry. It's been a long time since I've looked at these notes in this detail. Okay, sorry about this. If you look at what we have here, x naught to x for the outer integral, x naught to s for the inner integral. And what I want to do is, again, interchange the order of integration. And I'm not sure if I have an explanation in the notes for what I did. No, I didn't, so I'm going to need to add it. I'm going to make a note here to help you see what I did to change the integral from this to this. All right. So I have, in this case, s is some point between x naught and x. Now, x can be anything, but I'm going to assume for convenience that x x naught is less than or equal to x. It doesn't have to be true, but I'm going to make that assumption, and I should make that clear here. All right. But keep in mind, S has to be, because the outer integral is with respect to S. So S lies between x naught and x. So that means I have this relationship, that S is also less than or equal to x. Okay. Now, Z goes between x naught and S. So I have this relationship also. Yeah. All right, so that's how all the different variables here are related. Now, I'm assuming x naught is less or equal to x, and if it is, then I have this hierarchy right here. Now, the same ordering has to apply as I try to interchange the order of integration. So now I want the outer integral to be with respect to z. So I'm integrating from x naught to x in z, but keep in mind, s has to be between z and x. So that's why in the inner integral, s has lower limit z and upper limit x. And then z has lower limit x naught and upper limit x. So that's why this integral with these modified limits and the change order of integration is equivalent to this one. In a way, you can think of this double integral as being over a triangle, and that's something you'll learn more about in Cal 4. So we're dealing with the same triangle here. Okay, but it's this relationship, this ordering, that leads to this. Okay. Now, by changing order of integration, f double prime of z does not depend on s. It's constant as far as s is concerned. So I'm allowed to move this out here, outside the inner integral. So now I'm integrating 1 ds from z to x. So that just gives me x minus z. So now I have this form of a remainder, of the integral form. But again, that's not all that practical. But what I can do is keep in mind that z is between x naught and x. So what that means is this linear factor does not change sign between x naught and x. So what that allows me to do is use what's called a weighted mean value theorem for integrals. And here's a statement of it right here. If I have an integral of f of x times g of x, and g of x does not change sign on the interval of integration, then I can leave a g of x inside the integral, pull f out, but f is now evaluated at some unknown point between a and b. So if I use that in this case, before I had f double prime inside the integral, I pull it out, but now it's evaluated at some unknown point between x naught and x. But this integral, I can now evaluate, and I get x minus x naught squared all over 2. So this is the remainder in the first degree case. But keep in mind, we saw this expression like this earlier. If I go back to the general Taylor series that I wrote the first few terms of, this is a third term. And what you'll notice is that this is exactly the same, almost exactly the same, that is, as what we have here, except now the second derivative is evaluated at an unknown point. Okay. So as an example, we have f of x is sine x. So I want the first degree Taylor polynomial. So I evaluate sine x at 0, and then plus its derivative, which is cosine of x, also evaluated at 0, times x minus 0. Okay. Actually, it should make clear that that in this example, my center is 0. Now, sine of 0 is 0, cosine of 0 is 1, so all of this just reduces to x. So sine x is approximately x when x is near 0. So now the remainder would be the second derivative, which is minus sine of x, evaluated at an unknown point over 2 times x minus x naught squared, so that would just be x squared. So this is our remainder. Now, sine is less than or equal to 1 in absolute value. So suppose x is less than 0.01 in magnitude. So that would tell me that the error in approximating sine for x that close to 0 is going to be less than or equal to the upper bound on x squared all over 2. So this is the maximum possible error. So when x is near 0, this approximation of sine x by x is reasonably accurate. Now, I'm not going to go through the rest of this in detail because you can see how scary this looks. But I'm going to cut to the chase here. Yeah. Given what I've already shown you, this would be quite onerous, but at least you have a notes to look through if you're interested. But when you have, what it's saying is that you can approximate your function f of x by a Taylor polynomial of degree n plus the nth Taylor remainder. So this right here is the Taylor polynomial of n of degree n, that's Tn of x. And then this right here is the Taylor remainder, but in integral form. And here you see this kind of relationship between the various variables in your integrals. I already used this in the first degree case. But again, we prefer not to have integral form. We want something more useful than that. And that leads to, finally, the statement of Taylor's theorem. So this is Taylor's theorem. It states that if f has at least n continuous derivatives, and if the n plus first derivative at least exists on an interval AB, it doesn't have to be continuous. And if you choose x naught, your center, to be in this interval AB, then on this interval, you can express f of x as a sum of the nth degree Taylor polynomial and the nth Taylor remainder. So here is the nth degree Taylor polynomial, where I've written out the first several terms and also the last term. So all you're doing is you're evaluating all the derivatives of f at x naught from 0th derivative all the way up to nth, divided by n factorial, or j factorial, and then you're multiplying by x minus x naught to the jth power. Now, the error in that approximation of f of x by Tn of x is the nth Taylor remainder. And you can see that this closely resembles what will be the next term in the Taylor expansion. If I were to replace n by n plus 1 throughout, I'd have almost exactly this. Again, the only difference is that instead of evaluating the n plus first derivative at x naught, like we have here, is at some unknown point xc. I've written it as xc of x just because the location of this unknown point depends on x. It's some unknown point between x naught and x. And generally, we don't try to find out what that unknown point is. What matters is a range where it can be found, because then we can use that to try to figure out how large this can get, and therefore how large the entire remainder can get. So that's the idea. But we try to get an upper bound on the absolute value of the n plus first derivative. That gives us an idea of how large the remainder can get and how accurate of an approximation our nth degree Taylor polynomial is. All right. So Taylor's theorem that gives us that remainder. So as an example, revisiting e to the x, we look at the third degree Taylor polynomial. So that would be the first four terms of its Maclaurin series, because we're using 0 as the center. So then the remainder would be x to the fourth over 4 factorial times exponential of some unknown point, xc, where xc lies between 0 and x. So if I were to let x be equal to 2.5, then I can plug it in for x, and then I know that xc is between 0 and 2.5. Now I'm looking for a worst case scenario. E to the x is an increasing function. So the largest that this can get, if xc is between 0 and 2.5, would be, I get the largest value at xc equal 2.5. So I go ahead and work all this out, and I get this value. That's how large the error could possibly get. And that's quite large. We don't want to have we don't want to have error that large. That's about half the size of e to the 2.5 itself. Sorry, what I just said there was totally wrong. Okay. Sorry. E to the 2.5 is value of that is roughly 12. So the possible error is larger than e to the 2.5 itself. Sorry about my earlier flub. It's been a long day. So what this goes to show is that a Taylor approximation is generally only a really good approximation of your function for x near the center. The center in this case was 0. We've already wandered pretty far away from that. So what I'm going to do is change the center. I'm going to use the center x naught equal to 2. So this is the third degree Taylor polynomial with that center. So notice I have powers of x minus 2 throughout instead of just plain old x. And I have to evaluate all my derivatives at the center x naught equals 2. So that's why we have e squared in all of these terms. So now we'll get to remainder. E raised to an unknown point over 4 factorial, x minus 2 to the 4th power. And xc lies between 2 and x instead of between 0 and x. So once again, the largest that this can get is e to the 2.5, still divided by 4 factorial. But now, instead of raising 2.5 to the 4th power, it's 0.5 to the 4th power. So now the error turns out to be a whole lot smaller. So I have assurance that I can accurately approximate e to the 2.5 using this third degree Taylor polynomial, because my error is only at the very most about 3%. Actually, what I'm trying off screen is I'm actually going to evaluate this Taylor polynomial at x equal 2.5. Let's see what I get, because this is only an error estimate. The actual error cannot be larger than this, but it could be a lot smaller. I'm going to find out. So just plugging in 2.5, and I'm working this out in MATLAB. Oh, something went wrong here. Oh, okay. MATLAB was acting funny. Okay, so all right, so the I'll just make a note here. The actual error e to the 2.5 minus T3 evaluated 2.5 is roughly 0.0213. All right, so at least this error estimate was in the ballpark. So it turned out to be only about 2% error. All right. Next example. This is based on a homework problem. Whoops, typo there. Okay. Now, so here's our function, 4 e to the x plus 9 e to the minus x. So I want Taylor polynomials of degrees 1 and 2. So for that, I need the function value, its first derivative at 0, which is a chosen center, and then a second derivative at 0. My formatting is a bit off. Okay. So those are the values I need of my derivatives. So now I can use them to construct my Taylor polynomials. So for degree 1, I have f of 0 plus f prime of 0 times x minus 0. And I just fill in these numbers, and this is what I get. And then for T2, I have the same. The first two terms are the same as what we have here. And then I add on this term. So 1/2 times second derivative times x squared. Now, same exercise, but with a very different kind of function. I want a third degree Taylor polynomial with center x not equal 4 for this function. So I use the power rule repeatedly to obtain the derivatives that I need. Really, the general power rule, so power rule coupled with chain rule, and these are all my derivatives. But then I need to evaluate them all at x equal 4. And I need to substitute x equal 4 into the function also. So I get these values from that. So then I have my formula for the third degree Taylor polynomial. So f of 4, f prime, f double prime, all my derivatives evaluated at 4 times the appropriate power of x minus 4. And all the terms divided by the appropriate factorial. So 0 is factorial is 1, 1 factorial is 1. Here I have 2 factorial, 3 factorial. So then I work everything out, plugging in all the numbers that I have. And this is my third degree Taylor polynomial. I can see how many examples I have left. Oh, okay. Just one more. Now my function is e to the minus 6x. My center is 0. So whereas in the previous examples, I had specified up front what degree Taylor polynomial is required, here we don't know, or focuses on a remainder. We want to choose n large enough so that the Taylor remainder, in other words, the error, can only be this big on the interval where if x is chosen from the interval -1 to 1. So another way of putting it is I want the absolute value of Rn of x to be no larger than this for x on this interval. So here's the general form of a Taylor remainder for Taylor polynomial degree n. So n plus first derivative at some unknown point between 0 and x. Now, so because xc is between 0 and x, where x goes from -1 to 1, xc also must be somewhere in this interval. Now, if I take the n plus first derivative of my function, I can have -6 raised to that same power, n plus 1, times e to the -6x. So how large can this get when x is between -1 and 1? Well, to make this as large as possible, I want this exponent to be as positive as possible. So that would mean setting x equal to -1, thus giving me e to the 6. And then the largest is, and then this in absolute value is the 6 raised to the n plus 1. So now I want 6 to the n plus 1, e to the 6 over n plus 1 factorial to be smaller than this. Now, it would be nice if I could solve this inequality for n, but given the functions involved, we have a factorial here and a exponential function here. That's not something you can really do. So instead, you can use trial and error, plug in values of n, and what happens is this is going to be too large at first, but eventually this quantity will get smaller and smaller as n increases because factorial grows faster than anything up here, than this exponential function. Eventually, this will overtake it, but it takes a while. You need to set n equal to 20, at least 24, to make this expression smaller than 0.001. But again, keep in mind, it's only a good approximation when x is sufficiently close to the center, especially when the derivatives are large, and that's what we have in this example. Because we have e to the -6x, when you take derivatives, you're multiplying by 6. So when as x is going towards -1, this is already a pretty large number, so this is especially large. Okay, so that's all for this set of notes. And in the next pre-recorded lecture, I'll be going further with working with Taylor series, and in particular how to obtain them for certain functions. I should mention that I can imagine that what I was going through earlier up here could be quite difficult to follow. But on the other hand, this is the understanding of this is not needed for the homework. The homework is problems for this material are based on the examples that I have in these notes and also in the next set of notes. So if you didn't quite follow this, I wouldn't be concerned about as far as your grade is concerned. This is just for those of you who want to see how the remainder formula is obtained. Then this material would be of interest, so I wanted to include it.